This is James Clerk Maxwell, and we are going to learn in this lecture how he fixed Ampere's law. So, here we have a circuit consisting of a battery and a parallel plate capacitor. And we're going to flip a switch and allow the capacitor to charge. And over here, we have Ampere's law. And I've drawn an Amperian loop here. And Ampere's law says that if we integrate B dotted with dl around the Amperian loop, that should be equal to mu naught times I enclosed. However, we have always assumed that the surface of the Amperian loop would be drawn like this. But it does not have to be drawn like that. Instead, we could draw the surface like this. You can think of this as blowing a bubble, and the edge of the bubble is here on the Amperian loop. But we're making a surface like this. So you have your wire like this, and you have a surface like this. The edge of the surface is where the red circle is. But the wire does not penetrate that black surface. So here's the problem. If you look at the surface that I shaded in blue, which is the surface that we usually do, you have I enclosed for that curved surface being the current that's flowing in the wire. However, if you look at the black surface, there's no current, there's no wire penetrating the surface, so there's no current enclosed. And so Maxwell fixed Ampere's law by adding another term to it. So he said that for Ampere's law, you should have B dotted with dl is equal to mu naught times I enclosed plus mu naught times epsilon naught times the derivative of the electric flux with respect to time. Now, we saw the electric flux back in the very beginning of this course. That was E dotted with A, or the integral of E dotted with dA. We also saw the magnetic flux more recently, which would be the integral of B dotted with dA. So I'm going to put a subscript E here to remind you that this is the electric flux, because we are going to be looking at both the magnetic flux and the electric flux in this section. Okay, so this is the term that Maxwell added in order to fix Ampere's law, in order to account for the fact that no one ever told us that we had to draw the surface the way that we had been drawing it. So we should be able to draw it with the black surface, and the equation should still work. So now we'd like to check and see that this new equation does work. So let's look at the black surface that we have. So I enclosed is going to be equal to 0 because the current is not going through the surface. So this term is equal to 0. I have the integral of B dotted with dl then is equal to mu naught times epsilon naught. Those are both constants that we have seen before. Remember, epsilon naught is related to the constant K. And now I have to figure out what the derivative of the electric flux is. Well, we do have electric flux here because here's our parallel plate capacitor. I'm going to draw that again. And we have current flowing this way, which means positive charge is going to pile up on this side of the parallel plate capacitor, and we will then have negative charge on this side of the parallel plate capacitor. So positive charge is flowing to this surface. Well, actually, it's the negative charge that moves, but we can pretend the positive charge is flowing to this surface, and then positive charge is leaving this surface, which makes this plate negative. So if this plate is positive and this plate is negative, we would have an electric field pointing from the positive plate to the negative plate. in the region between the two plates. We will ignore what happens right at the edge of the plates, and we'll say we have an electric field in this region, and then outside of the parallel plates we have no electric field. So the area that we would use for the flux, remember that, the flux would be the integral of E dotted with dA. So the area that we have here would just be the area between the two plates, because that's the only region where we have an electric field. So that would be, for the dot product, if we say our area vector is pointing this way, this is not a closed surface. Remember, a closed surface divides all of space into an inside and an outside. That's not true with our surface here. And so we would have to define a positive direction for the area vector. So let's just say that positive is this way. And then when we do the dot product, we'll just have E dotted with dA. Now there's it's the magnitude of E and the magnitude of dA, and they're not vectors anymore. I need to know what the magnitude of the electric field is. Remember that for parallel plates, the electric field depends on the surface charge density, and you divide that by epsilon naught to get the electric field. So the electric field itself is sigma over epsilon naught, and then the area that is the same as the area of the plate, and sigma, that is the surface charge density, that's Q divided by A. So I can replace sigma with Q divided by A. That's over epsilon naught times A from the flux here, but then this A and this A cancel out, and I have Q divided by epsilon naught. Then I have to take the time derivative. This is the charge that is currently on the plate, but once you flip the switch, that charge is going to start increasing. So this charge is changing with time. So I have to take the derivative of the flux with respect to time. That's epsilon naught is a constant, so that could just come outside, and then I have dq dt. That is the rate of change of the charge, which is equal to the current. So this is just I divided by epsilon naught. Okay, so now I'm going to go back and put this into the new version of Ampere's law. So, so I left off writing this here. This term is 0. I still need to put in what I get for the derivative. That's what I had there. Okay, so that goes up there, and that's just the current divided by epsilon naught. But look at this. Epsilon naught cancels out, and then I just have mu naught times I. This is the current that's flowing in the wire, so that would be the same as I enclosed if you used the blue shaded surface to find the magnetic field. So no matter which surface you use, you get, if you use the blue surface, you would just have mu naught times I enclosed, and I enclosed would be equal to I. And if you use the black surface, we get the same thing. One more thing that we have to look at. If you did use the blue shaded surface here, when you calculate the electric flux, because we said we only have an electric field between the two plates, if you use the blue shaded surface here, then the electric flux itself is equal to 0, and it's not changing, so the derivative is equal to 0. Okay, so we have the blue shaded surface here, which gives us just mu naught times I, and then we have the black shaded surface, which looks like a bubble here, also giving us mu naught times I. And for reasons that I don't really think we need to go into, this I here is called the displacement current. It is another one of those unfortunate names which doesn't really tell you anything about what is really happening. So we don't really have a current flowing between the two plates. We have a changing electric field, and that is related to the displacement current. Okay, so that is how Maxwell fixed Ampere's law, and in the next lecture we're going to learn more about Maxwell.